This video we are going to be finding the maximum likelihood estimator for our parameter p. Now the probability mass function for our geometric distribution is given as this: p into 1 minus p raised into x minus 1. Now for us to find the maximum likelihood estimator, we firstly need the likelihood function. So the likelihood function it's gonna be the product from I equals 1 till n of our PMF, probability mass function. So I'm just going to write this likelihood as the likelihood of P. You can also write it like this, but I'm just going to write it like this for space. Now this is going to be P1 minus P into x1 minus 1 multiplied by P into 1 minus P raised into x2 minus 1 minus P xn minus 1. This is n minus 1. Sorry for that, because I no longer have space now. Now this, it's gonna be p times p times p, which will be laws of exponents. We're gonna add the exponents, so it's gonna be p 1 plus 1 plus 1 up until n. Now that is gonna be p raised into the exponent of n. P raised into the exponent of n. For this one, it's just going to be the product from I equals 1 till n of 1 minus p x I minus 1. Now the product of this, by laws of exponents, we are going to add the exponents. So this is just going to be the summation sum of our xi minus 1. Okay, now this is our likelihood function for our parameter p. Now the next step we're going to do, since we have the likelihood function, we're going to find the first derivative of this likelihood function. Now the derivative of this likelihood with respect to p, this will be, no, firstly we are gonna, no, before we take the likelihood function, we are firstly going to take the logarithmic function of this before we take the derivative. So ln of our LP. So we firstly need to take the logarithmic function of this. Now the logarithmic function of this, which will be n ln p, and then this one is a product, so it's going to be a summation of this. This will be we're gonna distribute the sum inside there, so it's gonna be sum of our xi ln 1 minus p, and then we are gonna subtract, because the summation is from I up until n. So now this will be n, so it's gonna be minus n ln 1 minus p. Okay, let me erase this since I didn't have space. Now to maximize our parameter p, we are going to need to take the first derivative of this and equate it to 0. So if we take the first derivative of our ln of our likelihood function and we differentiate it with respect to p, this will be n divided by p, and this one will be plus sum of xi's, derivative of this part, we are going to have sum of xi's divided by 1 minus p, and then we multiplied this by the derivative of the inside, which is negative 1. So now if we multiply that with negative 1, it's gonna be minus here, minus. Now the same thing as of this one, it's gonna be minus n divided by 1 minus p multiplied by the derivative of the inside, which is negative 1. So we are gonna be adding them. Now we've taken the derivative of this likelihood function. Now we need to equate this derivative to 0 to maximize this p. N over p minus sum of our xi's divided by 1 minus p plus n into 1 minus p. Now we need to solve for p. In this case, for us to solve for p, we are firstly gonna multiply the whole equation by 1 minus p. So 0 into 1 minus p is equals to n into 1 minus p divided by p minus sum of xi's into 1 minus p divided by 1 minus p. This will cancel with that, plus n into 1 minus p divided by 1 minus p. This will also cancel with that. This will be 0, equals n into 1 minus p divided by p minus sum of xi's plus n. Now I'm gonna multiply the whole equation by p. Now p into 0 equals np into 1 minus p divided by p. This p and this p cancels, minus p into sum of xi's plus np. Now I'm gonna have to solve for p. For us to solve for p here, we are firstly gonna multiply this n into this bracket. So what we have here, no, this is 0. 0 is equals, so n minus np minus p into sum of our xi's, and then plus np. This cancels with that. Now I'm gonna transpose this negative p into sum of xi's into the right hand side, and then I'm gonna have p sum of xi's is equals to n. Now I'm gonna divide both sides by the sum of our xi's. Divide both sides by the sum of xi's. Now our p is gonna be equals n divided by sum of xi's. Okay, now this is the same as 1 divided by x bar, since x bar is equals to 1 over n sum of xi's. So this is just the reciprocal of our x bar. So therefore our MLE p hat is going to be equals to 1 over x bar, which is the same as our moment of estimate.